In the last video, we discussed how the conformations of carbon groups around single bonds can affect the stability and energy of a molecule, and how we can show these conformations using Newman projections. One molecule comes to mind that has really interesting conformation: cyclohexane. Let's imagine cyclohexane as we do with Newman projections. Instead of viewing cyclohexane as a bond line, the 3D graphic is showing the perspective of cyclohexane from the side. However, the most stable conformation of cyclohexane exists when the bonds twist a little. This generates the most possible amount of space between the substituents on each of the carbons. This conformation is called the chair conformation. The name probably comes from the fact that this form looks like a chair. It also kind of looks like the Budweiser logo and the Messenger logo by Facebook. The chair conformation is the most stable conformer of cyclohexane and thus has the least potential energy. Cyclohexane can also form the boat configuration and the half-chair configuration. The half-chair configuration is the most unstable conformation of cyclohexane and thus has the most potential energy. The boat configuration is halfway in stability and potential energy between the half-chair and chair conformations. There also exists a twist boat conformation that not all courses mention. This conformation is slightly more stable than the boat conformation. This is a diagram that summarizes the stabilities of the conformations of cyclohexane in terms of potential energy. But what do stable and unstable conformations mean in the bigger picture? All that stability refers to is the most common form of a molecule in solution. For instance, if I were to pour cyclohexane in a beaker and use a hypothetical microscope to analyze it, most of the molecules, by a large majority, would exist in the chair configuration. This is simply because the chair configuration is once again the most stable form of the molecule. This goes for Newman projections and conformations of other molecules as well. Now that we can understand cyclohexane configurations, let's focus on the chair configuration. This course mostly focuses on the chair, as it is the most stable and thus the most abundant form of cyclohexane. It's worth practicing drawing the basic chair. Notice that each diagonal bond is parallel to one another, and the vertical bonds on either side are not completely vertical. There is one process in which a chair conformation of cyclohexane can undergo a ring flip. This 3D graphic shows how that process occurs. In a moment, we'll talk about what happens when a ring flip occurs. Remember that cyclohexane, as a cyclic alkane, has two hydrogens attached to each carbon. As a chair configuration, we draw these two bonds as axial and equatorial. Axial bonds are perpendicular to the plane of the ring and appear as up or down. Equatorial bonds extend diagonally from the plane of the ring, either diagonally up or diagonally down. We can also modify the basic cyclohexane by adding two methyl groups. In this example, I added one methyl on a wedge and one methyl across the carbon on another wedge. The following should be starred and highlighted in your notes. A wedge means the substituent is facing up, while a dash means the substituent is facing down. Dash and wedge do not mean axial or equatorial. They could mean either of the two, but they directly specify where it points. If we convert the cyclohexane to the chair configuration, we can put the methyl groups either both facing up on axial or both facing up on equatorial. Both would be correct, but what's the difference? The most stable form of a chair configuration exists when most bulky substituents exist on equatorial bonds. This exists because of something called diaxial interactions. When the two methyl groups both exist on axial bonds, they repel one another and cause a degree of instability. When the two methyl groups are on equatorial bonds, they're as far away from each other as possible. Earlier, we mentioned ring flips. So what happens to the chair configuration we drew when a ring flip occurs? When a ring flip happens, axial bonds invert to equatorial positions, and equatorial bonds invert to axial positions. Therefore, one good observation is that the most stable form of the cyclohexane we drew would be the one we drew first, before the ring flip. Like we spoke about before, since both substituents face up, we can also call the cyclohexane cis. Now you can see on the chair configuration, if both substituents face the same way, cyclohexane is cis, and if they face opposite directions, they're trans. In the past couple of videos, we kept mentioning stability and energy. And in the next video, we'll define a couple terms that will definitively explain how the differences in stability and energy come about. Practice the chair and conformations using the worksheets and answer keys, as well as the explainer videos linked in the description below. See you guys in the next video.